We will now look at high-dimensional structure given by higher homotopic groups pi n. Before that, just a quick comment about CW complexes. They gave us a way of constructing spaces which have higher dimensional structure, but that's really not how you should be looking at them. You should look at them as ways of describing spaces, in the sense that a lot of familiar spaces we would look at, from things like spheres and tori to spaces given by algebraic equations to spaces from linear algebra like Grassmannians and so on. All of them have CW complex structures. So this is really a way of describing spaces in higher dimensions, and if they're finite dimensional, typically also with the CW topology. Okay, but this lets us construct high dimensional spaces. We want to understand high dimensional structure, but we'll do very little here. So what happens with homotopic groups is they're easy to define. There's a bunch of things that's quite easy to do and useful, and then everything else is much harder. So we'll just do the easy part, but that is enough for us to see some things interesting. In particular, as I mentioned earlier, to say what it means to have no structure in dimension 2 and above up to homotopy in a subtle, non-trivial way. So we'll take that as the goal, to be understand enough of homotopy theory to that, and then we can look at Whitehead's theory for such spaces. So, well, what are these homotopic groups? They're just like the fundamental group. So we look at F, we'll look at the spaces of F. This time they'll map 0, 1 to the n to x. Okay, and so pi n, but pi n is going to be of x, x0. Again, as usual, it's a base space. So we'll need something similar to what we had earlier. Now the entire boundary of the cube has to go to x0. Okay, so let's look at this space. So on this space we have star, or it's defined plus for a reason that will become clear in a little while. So what we do is f star g is the following. So I have f, let's say this was in 2 dimensions, and I have g. I'll just stick them side by side like this on one side. So f star g is of well, now we have several coordinates, right? x1, x2, xn. Well, it's going to be dependent only on x1. So in case 0 is less than or equal to x1 is less than or half, we have a certain definition. And if half is less than or equal to x1 is less than or equal to 1, we have a different definition. And here this is f of 2x1, but x2 and xn are left alone. And here this is g of 2x1 minus 1, and everything is left as it is. So we are just sticking them side to side. Okay, so we have this, and we also have a relation which is homotopy rel boundary. Okay, so that is f is homotopic to g if there exists h. Now this is going to map 0, 1 to the n plus 1 to x, such that, well, at the bottom h of x1 xn 0 is f, h of sorry, I wrote equals 0, xn 0 is f of x1 xn. Now for all everything in the obvious domain, and h of x1 xn 1 is g. And remember, the entire boundary has, so the base is going to be f, the top is going to be g. The entire boundary, which includes the base, the vertical sides, and the top of the n plus 1 cube, is going to be x0. So more precisely the set x0. They all map to the set x0. Even here, to be precise, I have to say the set x0. Okay, so this is fine. I have gotten operation as well as a homotopy, and so definition pi n of x x0 is these maps, is maps f up to homotopy fixing boundary. So let me give this a little bit, write it a little better. I won't write it in all detail. So I can write this as maps from 0, 1 to the n, the pair and boundary of 0, 1 to the n. Okay, to x and space x0. Or if I wish, I could replace this by the singleton x0. So this is a pair of spaces to pair of spaces. This one goes here and the subspace goes to subspaces. This is just an obvious generalization of based spaces up to the relative homotopy. And so relative homotopy would be homotopy between pairs of spaces, which means at all times the boundary has to go to the boundary. This could be written, as I said, as above, as the simple h of the entire boundary is going to be x0, okay, with star as an operation. Okay, and I'll just put it here. It's quite clear that pi n of x0 is a group. It's clear given what we have already seen so far. So what we have to show is quite a few things. We have to show that the operation is nice, up to is associative, up to homotopy. The same proofs work. Rather, you can use the results and take the product with 0, 1 to the n minus 1. Also that you have identity, again up to homotopy, and use the constant map once more. And so the same goes with inverses. You mirror in the first coordinate to get the inverse map. And so this will give you the group operations up to homotopy. So just to say that again, the theorem we have is so A, let me put it this way, pi n of x0 with star is a group. More than that, it's functorial. And it's functorial in the homotopy category. So if I have x0 to y0 induces the map f star from pi n of x0 to pi n of y0. Okay, so previously I called my maps f, I'll call them something else, given by, if I have theta mapping 0, 1 to the n to, and as a pair, a boundary of 0, 1 to the n. So if I have given by this, if I have a map from this to x0, okay, I'm not going to put a parenthesis around, braces around x0, that's a bit pedantic. This gets mapped to f composed with theta, unless I mean the composition the other way. Yeah, no, it is this way. That is to say, I have f composed with theta that has the same domain, and it will map to y0. Okay, so it will map 0, 1 to the n and boundary of 0, 1 to the n to y0. Okay, so this is functorial. And secondly, if f is homotopic to G, rel base point f star equals G star. Okay, and so as usual you have the corollary. If x0 is homotopy equivalent fixing base point to y0, then the homotopy groups are all isomorphic. Then the pi n of x0 is isomorphic to pi n of y0 for all n greater than or equal to 1. It's even true for pi 1. In fact, it's probably true for pi 0 as well formally, but we won't consider that. Okay, so we'll see more non-trivial facts about higher homotopy groups, in particular the way they differ from pi 1 in a moment. But let me just sort of end with a picture, end this video with a picture. So you see, this fundamental group we can think of as a map from the interval which takes both endpoints to a single point. Okay, so this is a map from this to X, but you can think of it as a map from the circle to X. So we think of these as loops. Similarly, if I took a 2-disk and then I glued the whole boundary to a single point, what I get is a sphere. So it's nice to think of higher homotopy groups as maps from the sphere, and then the operation of gluing is going to be the one where you pinch a sphere along the equator or along a neck to get two spheres, and you take the map F here and you take the map G here. Well, it's useful to think in this way, that the maps are really maps from spheres, even though they're formally maps from the disk, but the boundary is collapsed to a single point.